Hello and welcome to this fifth video in my series on high-frequency electronic design with Microwave Office. In the first four of these videos, we looked at passive components and some of the aspects of passive components which I find are not often well appreciated. Now we turn to nonlinear circuits, mostly active circuits, and I would like to begin with a little bit about harmonic balance so that you understand exactly how it works if you don't already. And if you do, at least it puts us on the same page. That will then lead into the problem of setting up certain parameters in Microwave Office so you get a good simulation, a good meaningful simulation. Those parameters have to be set up. There is just no way you're going to get good results unless you understand what they are and you set them up right. So let's begin. Now, the main thing I want to talk about in these videos is methods to set up your problem optimally in Microwave Office. And for a linear circuit, that's no big deal. For a nonlinear circuit, it becomes a very big deal, and there's certain things you just have to know. And the first thing you just have to know is what exactly harmonic balance analysis is. Well, if linear circuit analysis is really simple, computers can do that without any problems or any special knowledge on the part of the user. But with nonlinear circuits, it's not that simple. Inevitably, you have to use some kind of an iterative technique in which you start with a rough idea of the solution and you improve it iteratively until it's finally good enough. So here's how we do that. We take the circuit and separate it into a linear subcircuit over here with all the linear stuff, resistors, capacitors, linear controlled sources, and all of that. And then over here on the right, we have the nonlinear subcircuit, which has all the diode junctions and diode capacitances and nonlinear controlled sources and all that stuff. Then at the interface, of course, we have voltages and currents. Now, I recognize that this might be a little bit misleading because I've shown this as having ports at the interface. Back in the old days, that's what we did, but more modern circuit simulators use a nodal interface instead. That's not really a big difference, but I think displaying it as ports, as I've done here, makes it intuitively a little easier to understand. Since it's a nonlinear circuit, of course, it will generate harmonics of the fundamental frequency voltage. So at each of these interfaces, we have a vector of voltages, which are the frequency domain harmonic components of the voltages, and we'll have vectors of the currents too, which are the frequency domain currents. And we'll have a bunch of those vectors, and we will have in both voltage and current. And so the trick is to find a set of voltages, which of course are our independent variables, which give us the same current in the nonlinear and in the linear subcircuit. Those currents, of course, are the dependent variables. So that's a problem that we have. Okay, so how do we do that? We start with an initial estimate of the voltages. It can be a wild guess. Very often it's just zero. And calculate the currents in the linear subcircuit. We then take these voltages and we transform them to the time domain because we have to analyze a nonlinear subcircuit in the time domain. There's no good, straightforward way to analyze nonlinear circuits in the frequency domain, unfortunately. So we take the voltage, the vector of all those harmonics, use a Fourier transform, convert it to a time domain representation. Then we can figure out the current in the time domain. And finally, we Fourier transform that and get the frequency domain currents. We can then compare these currents on either side of the interface, that is the linear subcircuit currents to the nonlinear subcircuit currents. And in general, they won't be the same. So we have to modify these voltages in some way that will get them closer to being the same. And if we can keep doing that over and over and over again, then we'll eventually converge on a solution. So how do we do that? We use a method called multidimensional Newton's method, and I'll show you a little about that now. Okay, let's take a look at the size of the problem that we've assigned to ourselves. Fundamentally, we're trying to satisfy Kirchhoff's current law at the interfaces and at each harmonic that we have in the circuit. That means we have a certain number of current conditions that have to be satisfied, and we have an equal number of voltages to do that. So we have, let's say we have some K harmonics, and we'll talk later about what that K should really be, plus DC. And we have N ports, of course, at the interface. And of course, the voltages and currents each have a real and imaginary part. So there's two parts for each one. Multiply those together, you get 2 times N times K plus 1 variables that you have, and I might add 2 times N times K plus 1 current conditions. So in effect, you're trying to solve a problem which involves this number of equations and this number of variables simultaneously, and if that's not bad enough, it's nonlinear. So, you think of how big circuits can be and how many harmonics you need sometimes. This can be a very big number. So how do we do that? Well, over time, people have proposed all kinds of different methods to do that. There are relaxation methods and some ad hoc methods. But the one that everybody centered on is called Newton's method, or sometimes in Newton-Raphson algorithm, and a multidimensional form of that. So let's take a look at that. This figure shows Newton's method in one dimension. Of course, we're dealing with multiple dimensions, but this is nice for just showing you intuitively how it works. Let's say we have some function f of x, and we want to find the zero of f of x, which is the point where it crosses the zero, or the value of x that gives it zero. It's still a very general thing to do. If you wanted to know, for example, where f of x is 5, you could just redefine the function as f of x minus 5 and find the zero of that. So it's very, very general and turns out to be very useful. Well, we're going to assume that we have a derivative of the function, df dx. So we make an estimate of the zero, and which is f of x0 here. And then we extrapolate using the derivative. We extrapolate down to the x-axis. That gives us another estimate of the zero, which of course won't be exact, but we can keep doing that, and you can see that if you keep doing that, you're going to home in on this zero pretty effectively. And it is a very efficient algorithm. Newton's method is quadratically convergent, and without getting into the details of what that means, it simply means that as you get close to this zero, it pulls in very quickly indeed. Okay, now what about our problem? We don't have one dimension, we have 2n k plus 1 dimensions, and of course 2n k plus 1 functions. So we have to satisfy those functions simultaneously with that large number of variables. And instead of the derivative of one function with respect to one variable, we have the derivative of that large number of functions. I'm getting tired of saying 2n k plus 1 if you hadn't noticed. And let's see, we have the derivative of that large number of functions with respect to that large number of variables. That gives us a matrix that is 2n k plus 1 in dimension. So we have 2n k plus 1, the quantity squared, number of terms in that matrix that we have to deal with. That's the number of derivatives that we have. We have to generate those, and then we stick them in a matrix. And then instead of a scalar quantity like this for estimating the zero, we have a matrix equation that does it. So we, at each step in this iterative process, it turns out we have to solve this big matrix equation. The matrix is called the Jacobian matrix. So when you deal with harmonic balance, you'll hear terms like Jacobian quite a lot. There are efficient ways to do that. You'll hear terms like Szymanski iteration and here's a real cool one, Krylov subspace processes. And if you get me in a good moment, I might explain what those are. But suffice it to say that those are methods that are used to make this problem simpler than it otherwise would be. Now, the next item on our list of essential things to deal with in setting up a harmonic balance analysis is the frequency set. Now, if you have a single tone problem, let's say you're analyzing an LNA and you want to see where it goes into saturation and you don't expect to carry the analysis past light saturation, a relatively small number of harmonics is fine. I usually just set the harmonic number to 8 harmonics and forget about it. That's probably more than you absolutely need, but on the other hand, it doesn't really cost you much more. Most single tone problems go very quickly, and it isn't going to make any practical difference if you pick 8 harmonics instead of 5 harmonics. Now, in a two-tone problem, it gets a little more complicated. What I'm showing here is the frequency components you get in a two-tone analysis when I've limited the number of F1 harmonics and F2 harmonics to 8 harmonics. So this x-axis is the F1 harmonics, that's 8 here, and the vertical axis is the F2 harmonics, which I call H2, which I've limited to 8 also. There are negative values of F1 because you could have, say, 2 F2 minus F1, and there's really no need to have the part of this plot that is below the x-axis because those frequency components are the same as ones from the upper part. So 3F2 minus F1 is going to be the same as F1 minus 3F2. It's just a negative value. And for the sake of frequency selection, they're the same. Okay, now, if I say, again, that we want 8 harmonics of F1 and 8 harmonics of F2, we get this frequency set, this whole big thing here. You may not really need that many frequency components, frankly. You may only need orders going up to 9 or 10 or even less than that. So what do you do about that? Well, there's an option in Microwave Office in the harmonic balance setup where you can say limit the order of the products. So if you were to tell it, say, limit the order to 6, everything below this line would be included and nothing above that line. Or if you said to limit to 4, it would be this line here. Everything below it would be included, but nothing above that. So that way you can make the problem a little smaller by throwing away harmonics that you don't need. This is less of an issue in many kinds of circuits like LNAs and that sort of thing. It's much more of an issue in mixers, and we'll talk about it with regard to mixers in one of the subsequent videos. Before I finish this, I should also define what I mean by order, since I used the term. Order is simply the sum of these absolute values of these harmonics. So if I had to say minus 3 F1 and 4 F2, that's this point here, that would be 7. 3 plus 4 is 7. So you just take the absolute value of the harmonic number. Now, I hope I'm not getting ahead of myself a little bit, but when you have a two-tone problem, you have to be really, really careful about the excitation frequencies and the harmonic numbers, because the higher harmonics in the Fourier transforms, when you have more than one tone, are often not very good. They're actually garbage a lot of the time. So if you are doing a problem where you want, say, 3F2 minus 2F1, you better have quite a bit more than 3 and 2 harmonics of those two respectively. And that has to do with the way the two-tone Fourier transforms work. And I don't really want to say much more of it beyond that, but you do have to be careful. Another thing you have to be careful about is the frequency spacing in two-tone problems. You can't say I want a 5 gigahertz excitation and 10 kilohertz spacing. It just won't work because the Fourier transform won't resolve those small differences. You really need to keep those fairly far apart. Another thing you need to do with the frequency spacing is make sure that a harmonic of one tone does not land on top of a harmonic of another tone, because the Fourier transforms really don't like that, and the harmonic balance process doesn't either. So be careful with that. You don't want to have, say, 4 and 5 gigahertz tones. If you have that situation, you can just offset the frequency of one of them to 4 and say, I don't know, 4.7, something like that, and it'll work a lot better. And I'll say a little bit more about this when I show you some examples. Now, there's one more thing which is absolutely essential to understand, and that is, how do we determine when the problem is solved? Remember, we are starting with a very rough estimate of the solution and improving it iteratively. At some point, we have to say, okay, that's good enough, and the problem is done. So how do we determine that point? Well, if you look at this stuff in a math book, the assumption is made that the condition is to reduce the Euclidean norm below a certain level. That is the root sum of the squares, or just the sum of the squares of all the components, all the current differences. And that doesn't work for microwave circuits. And it doesn't work because in a microwave circuit, we have a combination of very large components, like the output of a power amplifier, and we have very small components, like intermodulation products. Well, if you just took the norm, you would have a situation where you think that everything is converged when the smallest components are not, because remember, the larger components in that case are going to dominate the convergence process. So you have to have some method that takes into account both the large components and the smaller components, and that turns out to require quite a bit of thought. In Microwave Office, I think we have a very good way to do that. It's one that I came up with a long time ago, and it works very well. So it comes down to this. Suppose we took a look at the absolute difference between the current in the linear part of the circuit and in the nonlinear part of the circuit. So I sub capital N is a nonlinear circuit, and N is a vector component. That's a certain frequency component at a certain port. And the same for the linear component over here. If we just took the magnitude of that difference in milliamps or microamps, this would be pretty difficult because the intermodulation components are going to be on the order of microamps or even smaller. If you say that the large components as well have to be converged within microamps, the problem may never converge. You know, big power amplifier circuit, you may not get convergence to that very small current. So another thing that we think of is a relative error convergence criterion, and incidentally, we call this the absolute one over here. We call this a relative convergence, where we're looking at the difference between the currents compared to the average value. So this seems to work better in other circumstances. That is, it's perfectly reasonable to say that the large components, those power amplifier outputs and such, should be converged within 1% or 1/10% or something like that. But do you really need to have the small intermodulation components converged within 1/10%? That might be, you know, 10 to the minus 9, 10 to the minus 12 amps, which is neither necessary nor desirable because, again, you may have enough numerical noise that you simply cannot converge to that degree. So what do we do? Well, here's the way we do it in Microwave Office. We go down the whole list of frequency components and look at each one, and we calculate the relative criterion and the absolute criterion. And if the frequency component is converged according to either of those, we say, okay, that component is fine. And we go through the rest of the vector, and if all the components of the current error vector are converged to within one of these or the other, we say, okay, it's done. We've solved the problem. And you can set these up in Microwave Office, and you have to set them up in Microwave Office. You have to come up with some reasonable estimates for these things, or else you will end up with either a problem that gives you the wrong solution, or you'll end up with something that never converges. You know, we had a guy once who called support, who was very upset because his simulation wouldn't converge. And when the support guy looked at the simulation, he had these errors set to 0. And he called the guy back and said, you can't do that. And the guy said, well, I don't want any error. So that's kind of an extreme example, but that's the kind of thing that happens if you don't understand what the error criteria are. Now let's go to Microwave Office and take a look at a couple of simple examples. The first one I'd like to show you is a very simple FET circuit, which consists largely of just a FET and a couple bias sources and bias Ts to get DC into it. I use the Curtis FET model here just because it's simple, no other reason. So to do an analysis of that, it's best to do things hierarchically. So I have my basic circuit over here, and here I have kind of a test bed for it. In the test bed, I've taken my circuit, my FET subcircuit, and put it in here. And I've changed the default two-port representation to a FET representation, just so when I look at it, I can tell instantly what it is. The source is now a single frequency, but it is swept in power from -10 to 10 dBm and 2 dB steps. You do this by going to the port element panel, select port, double click on it to get here. It's a source, it's tone 1, fundamental frequency, and it's swept power. Well, that's really all you have to do, and then you can come over here and enter the start, stop, and step values for the sweep. Now, one thing we still have to do is to set up the options. All those things I talked about a few minutes ago, they're all right here. Now we're going to use the Aplax simulator, which is, it's really the better simulator. You can also choose the old AWR simulator from time, from ancient history. But the Aplax simulator is the one that it always defaults to. I recommend strongly you use that one. I've set it up for 8 harmonics. Since it's single tone, that's really all you have to worry about. That maximum order doesn't have any effect for single tones. And if we go down here to the convergence settings, I've set these to 0.01 or 1% for the relative convergence, and 1 microamp for the absolute error. The defaults for these, I think, are 0.1% and 10 to the minus 12 amps, which I think are a little tight, especially the 10 to the minus 12 amps. So I usually set it to something like this. You can always experiment with these things and see if the solution gets any better by making them tighter. I don't think it will, though. And that's all we really need to do. Let's sweep it. Take a look at the FET performance. And there it is. Swept power here. And you can see the output is starting to saturate a little bit. This was at 5 gigahertz, by the way. And there is a legend telling you that. Okay. So that's a simple single tone problem. It's very easy to set up, really. There isn't a whole lot you have to do, but they are things that you do have to do. Now let's try a two-tone problem and see how that works for us. I'm going to use the same FET circuit, but I'll use another top-level schematic to do the IM test. So here we are. Again, I have the FET here, and that's simply this subcircuit here, source and load. And I have this set up for two tones now, and you do it pretty much the same way that you set it up for one tone, which is you click on the port tab of the, after double clicking on the port itself, and select tones 1 and 2, excite fundamental frequency, almost always what you say, and I'm going to make it swept power, and of course it's a source. That's all you have to do. Now, this allows you to set up two tones with a constant frequency spacing. That's just what you need for an intermodulation analysis. There are more complicated ways to set up more complicated source arrangements. For example, in a mixer, you want two tones, but one will be at one source and one will be at another source. And you can do that. It's not quite as easy as this, but it's not particularly difficult either. Now, the important thing here is to set up the options. So let's go to options. I'll right-click on the subcircuit and the circuit schematic. And frequencies I've already set up for 5 gigahertz. It's just one frequency at 5 gigahertz. And let's go to the Aplex simulator, and you can see what the project defaults are. Now, this is something that really illustrates why you have to be mindful of the setup options. The default values for tone 1 harmonics and tone 2 harmonics are 5 and 2. In an intermodulation problem, there's no reason why you would have the two tones with different harmonics. They're both the same level, so why not make the same number of harmonics for each? And furthermore, in a mixer problem, you can see this would really be a problem if tone 1 is your RF and tone 2 is your LO, because you want a lot more harmonics of the LO because it's a larger signal, and that even 1 might be enough for tone 1 harmonics, and you have the opposite here, so that won't do. So let's set these up, and I'm going to make them 6 harmonics for each one. And that's pretty good. That's probably more than you need, but it should work. Now I'll go down here and look at limiting the harmonics. I'm going to limit the harmonic order to 6 as well, and that gives us that triangular truncation, frequency set truncation, that I spoke of a few minutes ago. And continuing on, the last thing that's really important is setting up the error and convergence settings. Again, the project defaults are 0.1% and 10 to the minus 12 amps, which is really, really tighter, I think, than it should be. Back when these things were first decided, I encouraged the guys at AWR to make these looser, but they never did, and I don't think it was a matter of disagreement, and it was more the fact that they had other things to think about at the time. And now if you try to change them, you might change somebody's simulation if he took the defaults for these. So if you make these looser, you know what's going to happen is that the customer support people are going to get calls from people who say, gee, I don't understand this, but my simulation has changed by just a little bit. And that might be the reason for it. So anyhow, we'll start up with 1%, and I'm going to make 10 to the minus 6 amps or 1 microamp for the absolute error. That's 1% for the relative error. And I think that's all we have to worry about here. Okay. So there's our simulation. I think we've got everything set up. And you know what I'm going to do? I'm also going to disable this FET performance measurement, which is our single tone simulation. And that way it won't, that single tone subcircuit here will not be analyzed. Let's try it. Surprised it took a second, but sometimes the first time you run it, it will. There we are. Let's take a look at our graph, output graph, and here we are. Here's our fundamental output, and here is our intermodulation product showing the typical 30 dB per decade slope that you expect to see up to the point where they saturate, run into some saturation. Now let's go back and take a look at this options, harmonic balance options setup again. You notice that I chose 6 harmonics for tone 1 and tone 2. And where did that come from? Well, it mainly came from experience. How do I know that's enough? Well, I don't really, it's just a guess. But about the only way you can test this to make sure that it's enough is to change the number and see if anything changes. So just for fun, let's make this 5 each. I'll leave the convergence criteria the same because, well, you can change those also if you wish. So let's try it again. And for all I can see, it's right on top of each other. So 5, 6 harmonics seems to be plenty for this simulation. So there is a 1-tone and a 2-tone simulation. When we talk about mixers and other kinds of circuits, it can get more complicated than this, but at the same time, the problem is not that difficult. That is, it's not that much more complicated. And the basic ideas that I've shown you here are ones that you will use when you get to those supposedly more complicated simulations.